Okay, let's take a look at another example where we're going to be using one of these double angle formulas in order to help us prove an identity. In this case, we've got cotangent theta minus tangent theta over cotangent theta plus tangent theta is equal to cosine 2 theta. So cosine 2 theta, that automatically makes me take a look at the list of double angle formulas that I have on the right side of my screen over here. But again, in this situation, there's 3 to choose from, and I'm not sure which one to pick at first. And the left-hand side of this identity looks more complicated anyways. So I'm going to start manipulating the left-hand side to see if I can get it to turn into one of these cosine double angle formulas. So we'll start with the left-hand side. And I'll begin by rewriting everything in terms of sine and cosine. So cotangent theta becomes cosine theta over sine theta. And tangent becomes sine theta over cosine theta. And I'll do the same thing in the denominator. So cotangent turns into cosine over sine. And tangent turns into sine over cosine. Now, in order to combine all of these fractions, I need to have common denominators. So that's going to be my next step, is to get all these fractions to have common denominators. In the numerator, I'll multiply this fraction by sine over sine, because that's what I see in the denominator over here. And then this fraction I will multiply by cosine over cosine. And then I will do the same thing with both fractions in the denominator, so that everything has the same common denominator. Okay, so now I'm going to write what I get as a result of all that. In the numerator, cosine times cosine gives me cosine squared. And then over here, sine times sine gives me sine squared. And there's going to be subtraction between those two things. And that will all be over the common denominator that I got, which is cosine times sine. And then in the denominator of this large fraction, I have something very similar. Cosine times cosine gives me cosine squared. This time there's addition between these two things. And sine times sine gives me sine squared. And again, the common denominator is cosine theta times sine theta. And now, since I've got common denominators in the numerator and denominator of my large fraction, I can go ahead and cancel those out completely and just focus on the numerators of both parts. So I'll have cosine squared theta minus sine squared theta over cosine squared theta plus sine squared theta. And at this point, both of those things look familiar to me. Cosine squared theta minus sine squared theta, that matches with the double angle formula for cosine that we have up here. Cosine squared theta minus sine squared theta. So the numerator has just turned into cosine 2 theta. The denominator is the Pythagorean identity, which means that our denominator is really just 1. So in our numerator, we've got cosine 2 theta, thanks to the double angle formula. And in the denominator, we've got 1, thanks to Pythagorean identity. And so that's it. Our goal was to show that it looked like a double angle formula for cosine, and we just did that. So now we're finished with this example. The other topic that I wanted to cover in this lecture is solving trig equations. And you guys have actually already done this a little bit by taking a look at what all angles have a certain trig value. For example, on our last test, I asked you to find all the possible angles that had a cosine of √3/2. And then you used your unit circle and looked at all the angles that had that value as the cosine. That is an example of solving a very basic trig equation. So we're going to use that strategy along with some other algebraic strategies that we're already familiar with in order to solve more complex trig equations. And it's basically a three-step process. You want to start by isolating the trig function, identifying all possible solutions for the trig function, which typically involves the unit circle, at least for our examples it will, and then express the solutions and take additional steps to isolate the variable if necessary. So let's take a look at a couple examples, and let me pull up my pen here. Okay, so the first step when you're solving a trig equation is to isolate the trig function. That means I need to isolate this part of the equation. So the first thing I'm going to do is add 1 to both sides, which gives me 2 sine 3x is equal to 1. Then I will divide both sides by 2. That will cancel this 2 in the front, and that gives me sine 3x is equal to 1/2. So that takes care of the first step. I've now got that trig function isolated. My next step would be to figure out what angles make that trig function a true statement. So in other words, where does sine have a value, or at what angle does the sine turn into 1/2? So I'm going to go ahead and use my unit circle, which I've got pulled up on the next slide here. So I'm looking for where sine is a positive 1/2. And sine is the y coordinate. So positive y values are in the first and second quadrant. And we're looking for a y value of 1/2. That happens, whoops, let me go back a slide here and pull up my pen. There we go. Okay, so y value of 1/2 occurs right here, and it also occurs right here. So there are 2 answers for this one, and for this example I'll express my answer in degrees. So it looks like 30 degrees would make this true, and 150 degrees would make this true. So now let's go back to our example, and we'll set up 2 equations. We've established that this part right here either needs to be 30 degrees or it needs to be 150 degrees. And if the variable was there by itself, then we would be finished. But it's not, so we have one more step to do. But in both cases, again, what we were taking the sine of needs to be one of these 2 angles. But in this case, if we're trying to solve for x, we need to go ahead and do one more step to isolate it, and that would be to divide both sides by 3. And so over here we would have 10 is equal to x, and over here we would have 50 is equal to x. So this equation has 2 solutions. Let's go ahead and try another one. I'll change my pen color here so it makes it easy to keep track of which problem is which. Alright, we've got tangent squared x is minus 3 is equal to 0. So again, our first step is to isolate the trig function. We would want to add 3 to both sides. That would give me tangent squared x is equal to 3. And at this point, anytime you have something squared and you're trying to cancel that out, you take the square root. So we would want to square root both sides. So tangent x is equal to, now what you have to remember at this point is when you are using square root to solve any kind of equation, you have to square root both sides. You need to put a plus or minus in front of your answer. So based on what we know about the symmetry of the unit circle, this one is probably going to have 4 correct answers instead of just 2, because there will be an answer in all 4 of the quadrants. So we've got our trig function isolated. At this point, we want to go to our unit circle and see which values would have square root of 3 for its tangent. And so let's go to the next slide. Oh, not the previous slide, the next slide. And see if we can find where we would have a tangent of the square root of 3. Now the tangent values don't directly show up on our unit circle, so we do need to do a little bit of calculating to figure this one out. But there's actually an easy way to remember this. I know that the tangent values come from taking the y-coordinate and dividing by the x-coordinate. And we want our result to end up being the square root of 3. And if you remember from our previous unit when we were finding tangents of these angles, since the denominator of these fractions both match, the denominators end up canceling out anyways. So if we want to end up with a result of square root of 3, then we need that result to be in our numerator, which means we need to be the square root of 3 to be part of our y-coordinate. So out of these 3 coordinates to choose from, this one is the one that has root 3 as part of the y-coordinate. And if I went ahead and did the calculation for the tangent of that, that would be square root of 3 over 2 over 1/2. So it's the y-coordinate over the x-coordinate. And these matching denominators, we can just get rid of those, which leaves us with the square root of 3 on the top and 1 on the bottom, which of course simplifies to the square root of 3. So all the places on the unit circle that have a y value of root 3 over 2 are going to end up giving us the correct angle measurement that we need. And I'll go ahead and express my angles in degrees again. So it looks like 60 degrees would work. And since it's okay for us to have a negative value as well, 120 would work. Looks like 240 would work. That's got a y value of root 3 over 2. And 300 would work. That's got a y value of root 3 over 2. So we've got 4 solutions, 60, 120, 240, and 300. So let's go back to our example. I'm going to write those down: 60, 120, 240, and 300. That's all the values where the tangent of that angle gives us plus or minus root 3. Now the one thing that I need to add that I didn't on the previous equation is how to show all possible angles, meaning these are the correct angles within one revolution. But if you add on revolutions, you're going to get to the same location on the circle and therefore have the same value of tangent. So for each one of these, I'm going to show that I can add any number of revolutions and still have the same value. If I were to do that same thing for the previous example, then I would need to go back to where I originally found the angle measurements before I isolated the x. And so let me get rid of some of my work here. And I'll show you where in this problem we would have taken that step. There we go. Okay, so at this point where I identified my 2 angles as 30 and 150 degrees, this is where I would need to show that I can add multiple revolutions and still end up with the same answer. And so next to 30, I would write plus 360n, and plus 150 I would write plus 360. And then I would still set both of those equal to 3x. I'll just put the 3x in the middle there. And so my next step would still be the same. In order to isolate the x, I would divide both sides by 3. I just need to make sure that I divide what I just added on by 3 as well. So my final answer now would turn into 10 plus 120n and 50 plus 120n. Alright, let's take a look at a couple more examples, and then you should be pretty much ready to tackle the homework assignment. Okay, so here's a chance to choose one on your own. I've got some multiple choice options listed, so if you want, now would be a good time to pause the video, see if you can solve this equation and identify which solutions belong with this equation. Otherwise, I'm going to go ahead and work through this example and figure out which answers are correct. And it looks like this time our answers are in terms of radians, so I'm going to make sure and look at the radian answers on the unit circle. So to solve this equation, I need to isolate the trig function first. So first I would add 1 to both sides. That would give me 4 cosine squared 2x is equal to 1. Then I would divide both sides by 4, which would give me cosine squared 2x is equal to 1/4. And then I would take the square root of both sides. And that would give me cosine 2x is equal to 1/2, since the square root of 1 is just 1 and the square root of 4 is 2. So I've got the trig function isolated. It looks like I need to look on the unit circle and figure out which angles have values of cosine that are equal to a positive 1/2. So I'm going to go back to the unit circle, and I'm looking for x values of positive 1/2. And it looks like I've already had those solutions show up in a previous problem. Here we go. Here we have an x value of positive 1/2. And x values are positive in the first and fourth quadrants. So I want to look down here. There's our other value of a positive 1/2. So it looks like pi over 3 and 5 pi over 3 would be our solutions. So that means that this part, 2x, is equal to pi over 3, and 2x is equal to 5 pi over 3. And to show the multiple revolutions, this time instead of adding 360n, I would want to add 2 pi n so that I stay within the same units. 2 pi n. And then there's one final step in order to isolate the x, and that's to divide both sides of the equation by 2. So in my choices, I'm looking for options that have only a pi n instead of a 2 pi n, as these numbers are going to cancel out. So that automatically gets rid of half of my choices. Then I want to look for angle measurements that show my original fractions but half of their value. So for example, if I divided pi over 3 by 2, then that would give me pi over 6. So this is one of my solutions. And then dividing 5 pi over 3 by 2 results in 5 pi over 6. So it looks like that option is not listed. But if I were to scratch out this 2, then that would mean that that would be the correct answer. So for this multiple choice question, there was more than one answer possible, but only one correct answer was listed. Okay, that takes care of some of the examples that we would have covered in class. Now would be a good time for you to try the homework assignment. There are additional tutorial videos to go along with that assignment, so if you get stuck on anything, then I recommend either rewatching this video or checking out the homework videos for additional examples. There's also going to be a Moodle quiz that you need to take care of, and that one will focus on simplifying trig expressions rather than proving these identities. So if you have questions over the weekend, shoot me an email. Otherwise, come visit me during office hours, and I will see you guys on Tuesday.